What are the requirements for life in the universe? Perhaps it is a fussy, punctilious phenomenon, one that only occurs in the rare cases where conditions are absolutely perfect. An event that demands each and every molecule to be precisely aligned. Or perhaps life starts with relative ease, just throw together a few random organic molecules and life inevitably spawns. Each of these possibilities is broadly consistent with our current data of life, which really is just us. All life on Earth is genetically related, distant cousins harkening back to a single microbial ancestor known as LUCA, the lowest universal common ancestor. So despite the biodiversity that we see today, we're all just descendants of this one success. Maybe there were others that eventually fizzled out, but for now, we have no evidence for such a claim. Crucially, the fact that there was at least one success doesn't actually teach us anything, because we already know that. Of course there had to be one success, else how could you and I even ponder such questions? Life could be incredibly rare in the universe, and if so, it's no coincidence that we happen to live in one of the rare places where it happened, because for living things such as ourselves, it could simply be no other way. This means that our mere existence, nor indeed that of the entire tree of life, does not help us in trying to answer this grandest of questions. How often does life get started? If we were to one day discover a second tree of life, then that would prove that life started at least twice. More importantly, that second start would have nothing to do with us. Our existence is not dependent upon whether it happened or not. Such a discovery would break the ambiguity. It would likely be the most important scientific discovery in human history, proving that we're not alone. Of course, there has been many claims of life throughout the years. Living seas on the moon, engineered clouds on Mars, fossil-like Martian meteorites, Venusian biosignatures, and of course, claims of alien contact or sightings. Yet none of these past claims have crossed the scientific bar needed to call them a definitive discovery, a reproducible set of observations with an unambiguous interpretation. The Martian canals is a particularly interesting subject that we've discussed in detail on this channel before, illustrating how easily our human preconceptions can interfere with an objective analysis of data pertaining to alien life. Of course, an absence of evidence is not evidence of absence either. Life could be incredibly rare or very common, or anything in between. So again, our existence in of itself doesn't provide any useful information here. In fact, trying to use it in such a way actually forms a circular argument, because of course our ability to ask these questions is predicated upon at least one success. A much better piece of evidence is the timing of when life emerged on the Earth, occurring cosmically quick within just a few 100 million years. In one of our previous papers and videos, I showed how this quick start is also still burdened with ambiguities, yet overall, it suggests that if we had the ability to somehow rerun the clock on Earth another time over, then we'd give 9-to-1 betting odds that life would indeed re-emerge quickly once again. If you're comfortable calling 9-to-1 a safe bet, then this single data point seemingly settles the debate, right? Rerun Earth's clock over again and life would re-emerge. Therefore, life should be common across the universe. Well, it's that second step where we need to tread very carefully. Because remember, I'm rerunning Earth's clock here, so that means that a planet with essentially identical conditions to the Earth, the same orbit, the same mass, the same initial atmosphere, even the same locations of each and every pebble on the planetary surface. But if I move one of those pebbles, or one of those volcanoes, or one of those continents, does that screw things up? Like the butterfly effect, perhaps even a small change might drastically change the fate of life to a potentially far more dire outcome. This is where the famous rare earth hypothesis comes in. First formulated by Professors Peter Ward and Robert Brownlee, the rare earth hypothesis has now become a highly influential and debated topic in astrobiology. As the name suggests, it argues that the conditions of our planet are incredibly unusual, finely balanced just right for life. If true, the idea that life starts quickly with Earth-like conditions becomes almost irrelevant because those conditions themselves are so rare that life hardly ever gets a chance to get going. Or a different take on the idea, and one that is more consistent with the original formulation, is that precise Earth-like conditions are necessary for intelligent life in particular. Perhaps there's microbes on Mars, but if you want a civilization, you really need something that's very similar to us. So what exactly is it that Ward and Brownlee suggest to be so special about our home? There's the fairly obvious ones like mass and size. Too small and the planet's gravity weakens so much that it can't hold on to a substantial atmosphere. Too heavy and the planet's higher gravity risks runaway growth into a giant planet. The next obvious factor is being the right distance from your star that liquid water is stable on the surface. When the book was published in 2000, well, we really didn't know much about either of those factors. But of course, in the years since, exoplanet discoveries have amassed, and now we finally do have some insights. For example, we now know that rocky planets are common around typical stars. However, we still don't yet know how common are rocky planets on Earth-like orbits around Sun-like stars. You can check out our previous video to learn why. Rare Earth goes much further than just mass and orbit though. To gain some insight, I'm going to highlight 4 key additional factors that are often invoked by rare Earth proponents. Factor 1. A habitable planet needs to have a magnetosphere to protect it from high energy radiation. This effect is coming into recent focus as we consider sending astronauts to the Moon or Mars on a long-term basis. The Earth's magnetic field protects us from ionizing radiation, deflecting charged particles along its field lines. Since the Moon and Mars don't have an intrinsic global magnetic field, this ionizing radiation poses a health risk to astronauts, leading to cancerous cells and radiation sickness. Of course, one solution is for astronauts just to hunker down under some regolith, either in caves or thrown sandbags on top of their base. In fact, the Earth essentially does this for us by virtue of its much thicker atmosphere. Indeed, renowned astrobiologist Jim Casting has argued that Earth's thick atmosphere is in fact sufficient to protect us even without a magnetic field, an idea which has support from the fact that life clearly persisted during Earth's frequent magnetic pole reversals. So, perhaps the field isn't so crucial after all. Moving on, factor 2 is that plate tectonics are necessary for life and may also be rare. The main thrust here is that biogeochemical cycles of rock, nutrients and chemicals are enabled by the subduction of crust. When an oceanic plate subducts under a continent, we essentially recycle chemicals locked up in rocks, the fossils and oil. The elements within them are liberated under the intense heat and eventually re-emerge through volcanic activity. It is thought that this recycling is an advantage for biology, maintaining a fresh supply of life's key ingredients. However, here too there's been pushback, some arguing that Earth mass objects inevitably form plate tectonics and that even without it, you can still have active geology. For factor 3, we turn to our moon. Our moon is freakishly large compared to the planet that it goes around. Whereas most moons in the solar system are no more than 1/10,000th the mass of their host planet, our moon is 100 times greater at over 1%. A consequence of this is that it has an oversized gravitational influence on us, most noticeable through the tides. But going deeper, it's also thought to stabilize the axial tilt of our planet, which is locked in at an angle of 23.5 degrees. It was Jacques Lascar who advanced this idea in a seminal paper in 1993, but since then, astronomer Jack Lissauer has pushed back, suggesting that stable obliquities can occur without a big moon too. A large moon could help in other ways too, such as generating huge, continent-covering tides shortly after its formation, and perhaps even kickstarting plate tectonics via the giant impact that formed it. But in both cases, it's deeply unclear how crucial these are for life. The final factor I'll discuss is death from above. impacts from comets and asteroids that could extinguish life on the Earth. Clearly, too many of these is bad for life, although it's also been suggested that not enough is a problem too. Perhaps, sometimes, evolution gets stuck in a rut and needs a clean slate, a reset to make progress again. In this context, Jupiter has been suggested to play an important role, perhaps protecting us from giant impacts. For example, in 1994, we watched from the Earth as Jupiter took one for the team as the 1.8-kilometer Shoemaker-Levy comet smashed into it. However, simulation work doesn't provide such a clear picture. In fact, astronomers Horner and Jones found that Jupiter actually led to more meteorite impacts on the Earth, not less. So as you can see, there has been considerable pushback about the validity of these individual factors. Now, rather than doing a deep dive on each of these, I think it's more useful just to ask, how can we combine these together? Can we somehow use them to calculate just how rare Earth is? It was John Cramer who suggested that factors like these could be combined together to build a so-called rare Earth equation. It computes the number of Earth-like planets in the galaxy, NE, as a function of the various inputs. So, as an example, we could write something like this, where Fp is the fraction of stars with planets, Fr is the fraction of those planets that are rocky, Fh is the fraction of those planets that are in the habitable zone, Fm is the fraction of those with a large moon, and Fj is the fraction of those with a Jupiter-like companion. 5 factors, and yes, I'm ignoring the geology factors in this example. Notice that by construction, each one is a subset of the previous. So Fh, for example, is not the fraction of all planets in the habitable zone, but rather it's just for the rocky ones. This is known as conditional probability, and it's going to be important to remember. Now, this sequence of multiplicative conditional probabilities very much resembles the famous Drake equation, which calculates how many civilizations are in the galaxy. In fact, the relationship is even deeper because the Drake equation has an explicit parameter for the fraction of planets that are Earths. So that means that we could replace this one Drake term with the latter 4 factors from our rare Earth equation just like this. In effect then, the rare Earth hypothesis can thus be seen to kind of expand that single parameter, eta Earth of the Drake equation, into a myriad of finer grained parameters that are necessary for true Earth analogues. I think presented like this, it ostensibly seems like an upgrade, right? We're improving the Drake equation, we're posing a refined mathematical version of it. But is that really true? Certainly, one advantage of this mathematical form is that it's very flexible. Look, you might disagree that a large moon is necessary for life, but instead think that a sun-like star is needed. Okay, fine, you can easily just swap out that factor in the equation, which would still leave you with 4 rare Earth factors. That would give us this equation, which we'll call scenario A. Alternatively, perhaps you think that the Earth is a far more rarefied and finely tuned concept than these 4 factors alone can allow for. Perhaps you add on a parameter for the solar system's galactic location, and then another for the planet's initial atmosphere, and then another for the land-to-ocean ratio, etc., etc. Eventually, maybe you end up with a list of, say, 80 factors, 80 distinct properties that are all simultaneously necessary for a planet to be truly habitable. Let's call this scenario B. So what is the effect of having 4 factors in scenario A versus 80 in scenario B? Well, for simplicity, let's imagine that each of these factors has a 50% chance of being true. So for example, the first factor is the probability of a planet being rocky, which is 50%, which coincidentally is about the right answer. In scenario A, we have 4 rare Earth factors, so the final probability of getting an Earth is 1/2 multiplied by itself 4 times, which we can write as 1/2 to the power of 4. Working that out, that gives us a final probability of 1/16 or 6.25%. Okay, so unusual but not extremely rare. Now let's try scenario B. With 80 factors, we have to do 1/2, but now to the power of 80, which equals 1 in a trillion trillion, or 10 to the power of minus 24. That's a number so ridiculously small that even considering every single star in the observable universe, you still wouldn't get a single other Earth. Of course, the choice of a 1/2 probability in that example was entirely arbitrary. The real point of that little exercise was to highlight just how important the number of factors we include in the equation are. I think often we get hung up arguing about the values of those individual parameters, should they be 1% or 10%, but in actuality, it is often far more important to argue about how many parameters should go into that equation in the first place. Now, of course, we don't really know how many factors to include. Remember that these factors are intended to describe the different conditions necessary to make a planet capable of supporting life. If we had a proven universal theory for the origins of life, then we could figure out the necessary parameters on the blackboard ab initio. But we don't. We know hardly anything about how life began. In the absence of that, one might try looking at our own planet as a single data point and trying to extrapolate, reverse engineer what the conditions for life in the universe truly are. Of course, trying to extrapolate off a single data point is incredibly precarious. And indeed, this is what many critics have suggested that Ward and Brownlee are really doing. And whilst they have reasonable arguments for the factors they consider to be relevant, we've seen how there's considerable debate about them as well. Furthermore, there's no way to test these claims until we start detecting life elsewhere in the universe. And I think this is where my own concerns come into focus. The whole philosophy of reverse engineering ourselves as an idealized example of life in the universe is inherently anthropocentric. It tacitly endorses a narrow perspective, one that assumes that the way things happened here is the only way which intelligent life can emerge, that our experience, our history, is the sole channel through which sentience can blossom. And look, we're all often guilty of this in day-to-day life. We base much of our philosophy of life upon our own direct experiences, ignoring the very disparate, often painful experiences that our fellow human being is voyaging through. A full understanding of life, both individually and in terms of biology, requires a larger view, a wider perspective. That might sound like I'm waxing a little over-philosophically here, and sometimes I'm indulgent of that, but let me just illustrate a specific mathematical consequence of this when it comes to the origins of life. Look, I can buy the argument that the origins of humanity are indeed the product of a series of highly improbable events. First you need X, then you need Y, and then you need Z. And as we add more and more terms, yes, I agree, the probabilities become vanishingly small. But crucially, that recipe may not be the only path to intelligence. There may be entirely separate, disparate avenues to arrive at a civilization. So, for example, even though a hypothetical world might never have had a magnetosphere, it was a moon orbiting a giant planet and thus protected by the giant's magnetic field instead. A completely alien setup, yet one which nevertheless could eventually lead to intelligent life. Equations like the Drake equation and the rare earth equation assume an inherently monolithic, singular pathway. Because remember, each term in that equation is conditional upon the previous one, forming an ever-narrowing funnel towards something which increasingly looks like us. But really, the search for intelligent life in the universe isn't just a search for our doppelgangers, it's far broader than that. And so perhaps we should imagine adding some parallel paths to those equations. For example, let's imagine that the planet had failed to form a large moon. That doesn't mean that the doors to intelligent life are closed. In fact, that closed door might open up another one, another pathway towards intelligence that is distinct and alien to that of our own. In this way, we would have to add parallel versions of the equation to itself. We no longer have a series of multiplying factors. No, now we have a sum of a series of multiplying factors. Perhaps there's a few paths, maybe just one, or perhaps there's a countless number. We simply don't know. And so, because of this, I personally don't subscribe to the rare earth hypothesis. Now, you might jump to the conclusion that I therefore believe there are lots of Earths out there, right? I mean, if I don't believe in X, then surely that means I believe in the opposite of X, right? Sadly, that's often become the kind of dichotomous logic that the modern media often tries to drum into us. But it's a false dichotomy. In science, it's okay to remain agnostic about a question until evidence is presented either way. And right now, we have no evidence, so I indeed withhold my belief. I'm not a skeptic, I'm not an advocate, I just await the result with keen interest. As I've spoken about on this channel before, I think this philosophy is deeply important. Consider that you tell yourself and others that you believe in, say, the rare earth hypothesis, despite the fact we have really no compelling evidence for it. Okay, fine, but now you face a possible day of reckoning when the data comes in and maybe you see that you were wrong. And so often, there is nothing that we find harder in life than to admit that we were wrong, especially if we express that view publicly. Instead, there is a tragic tendency to manipulate the information, to devise ever more elaborate narrative-fitting interpretations, and to seek out any snippet, any soundbite we can find to agree with our initial preconception, even sometimes at a subconscious level. Because admitting that you were wrong feels bad, but believing that you were right feels good. And look, in a way, I don't really need to tell you this because, hey, we all live in this modern era. But the real point is that even in astronomy, when it comes to questions such as how often life begins or the abundance of civilizations in the universe, we have essentially no data. And so, it's okay to withhold your belief until you see evidence either way. You don't have to plant a flag on issues with no data. We'll get to the data on this one day, but it may be a very long road ahead of us. And yet, when that day comes, let's make sure that we leave our anthropocentric bias, our preconceptions, our faith at the door, and just listen to what the universe is saying to us with open ears and clear eyes. So until next time, stay thoughtful and stay curious. Hey, thank you so much for watching this video, everybody. This video was supported by our Cool Worlds donors. In fact, I want to thank two of our latest supporters. That's Joseph Alexander, and a special thank you to one of our new Illuminati level donors, that is Mike Headland. Thank you so much for your support. If you too want to help us out, you can click the link up above and get access to special perks. And until next time, see you around the galaxy.